People the stork.
Maggie the she-bear, hello.
Hi.
Maggie, listen, help me out. I have here these orange circles and these blue circles, but I do not know if I have more orange circles or more blue circles.
People, have you tried to count them? Let's do it together.
1, 2, 3, 4, 5, and 6. There are 6 orange circles.
1, 2, 3, 4, and 5. There are 5 blue circles.
Maggie, but which number is bigger, 5 or 6?
I do not know, people. How can we find out?
Maybe I can help.
Santa.
Ho ho ho! As you will see, counting is all about one-to-one correspondence. Try to match orange and blue circles one-to-one.
We will try, Santa. 1, 2, 3, 4, and 5. But Santa, there is one orange circle left.
Exactly. So there are more orange circles.
That is brilliant. So let me see if I follow the principle correctly. I have here some green circles. I match them 1 to 1 with blue circles. So the number of the green circles is the same as the number of blue circles. We already know that there are 5 blue circles. So without ever counting the green circles, I know we have 5 of them. That's just brilliant.
Let me have a go. I'm matching these red circles with what we have, but I cannot cover all. So I know we have fewer red circles. I don't know the exact number, but I know it is less than 5. Maybe 4, maybe 3, maybe 2, or maybe 1. These all are numbers smaller than 5.
Now you are getting it, kids. You have 3 red circles there, and 3 is indeed less than 5. Nevertheless, 3 and 5, or any other number for that matter, are just names, like Pippa and Maggie. But what they represent is a class of objects that have one-to-one correspondence between them. And it does not end there. Let me magic up infinite sequence of yellow circles. It's never ending.
Wow.
And let me magic up an infinite chessboard of circles. You have to imagine it extends in 2 dimensions.
I'm in awe.
Me too.
Where do we have more circles? In the sequence of yellow circles, or in the infinite chessboard of circles?
Chessboard.
Chessboard, it seems.
Kids, I know how it looks, but the look might be deceiving. Remember, counting is all about one-to-one correspondence. Shall we try that?
Well, Santa, since it is an infinite chessboard, if I pick circles from the first row, I will never move to the other row. There must be more circles in the chessboard.
A nice attempt, people. But proving that something is impossible is not as easy as to find that something is possible. Your way does not work. But how do you know there is no other way that works? In fact, here is one that works. Let me pick up the chess pieces diagonally. Clearly, you can pick any piece on the board and, regardless how far it is, eventually I will get to it, while I will never exhaust the yellow circles that I am pairing with them.
I think we have just proven that all infinities are equal.
Proving something is much more than that, but you are right that I do not see how there could be a bigger infinity.
Not so fast, fellows.
Cantor, is it you?
It is I, Cantor, your most trusted reindeer. You claim that all infinities are equal. So let's suppose that I can arrange sequences of circles that change colors into a sequence. You see, two sequences are the same only if they follow the exact same color pattern. These two sequences follow it, but these two are different. Just one difference at one position is enough. And I suppose I have all these different sequences arranged here in a sequence. If all infinities were equal, then that would be possible.
Indeed, one-to-one correspondence. Ho ho ho!
But what if I now create a sequence of colors that is not here in this arrangement?
Impossible! All of them are there.
Yes, people, we assume that all of them are there. Yet, if I pick the first sequence and change the color on the first position to something else, and then I pick the second sequence and I change the color on the second position to something else, and I keep going like this to infinity, then I have created a new infinite sequence of changing colors that is different to every color sequence we have had here arranged. This is impossible.
Unless, ho ho ho, the original assumption is wrong. Cantor, you have proven that not all infinities are equal.
Eureka!
Ho ho ho! Let me recap, kids. Counting is all about one-to-one correspondence. This is true even when we talk about infinities. But not all infinities are the same. Ho ho ho!